We now move from Chile to the north and a little bit to the east to a country in Bolivia, where the case study for our last presentation is there. And we'll talk there about a new technology that was demonstrated with a load test. So we have all kinds of different ways of testing, with soil investigation, where it is monitoring, but now it's going to be with a load testing to show that this technology works. Mario, the floor is all yours.
Yeah, thank you. Normally it helps. Yeah, thank you. Okay, I will start to present a case study where we use the expanded bodies even for a high-rise building. For us, 34 stories is still the highest building in the city. Now it's being built a 40-story building also with the same technology. So the idea in this project, it was a quite big project because the yard is about 14,000 square meters, about 150,000 square feet, with two towers, 34 stories tall each one. Because of the performance of the tower, the settlements were limited, so it was important to find a stiff solution in order to achieve this need. In this case, we used two types of piles. One was the full displacement pile for the lower loads, and the other one I will show are the partial displacement piles with expanded bodies. And here I mentioned as a function of the cost per ton. For this project, we analyzed more than 10 alternatives, from large diameter piles to micropiles in some areas, and in CFA, partial displacement piles. So at the end, we got the solution using the criteria of cost per ton, which is at the end what the client always buy. They need to solve a weight problem, not a price per meter or cubic meter. And so the implementation was very successful. I will show you then this is the solution, where we have 406 piles with expanded body, and I think it's 700 small piles. The very important thing in this type of piles, mainly the full displacement pile, is that first the machinery give the records of several parameters. We use the Bauer systems, and then you have a higher use of the friction. The specific surface in smaller diameter piles is much higher, so you can get the benefit of that. We don't have severe earthquakes here, so that's not a problem. The main dynamic question is about wind. We would normally have winds not of standard, but measure 100 kilometers per hour as a normal thing every year. In this case, we could convince the client to perform a really good soil investigation. We performed 14 CPTU, 8 SPT, 2 dilatometers, 4 pressure meters, and 2 surface wave profiles. So with that, we could really find the difference. Even so, it's not perfect, because if we compute the volume of soil we have studied, is neglectable against the real soil volume. But we could really understand how it varies, the strength and the stiffness, the layers, how they will behave under such high loads. This is just a plan where the indication of each type, but I use this presentation of the CPTU because the site was clearly divided between the east and the west side. As you can see here, we have these soft soils in the upper part, followed by sands and silty sands, quite dense. In the other case, we had the problem that the sands and silt sands were in the upper part, but not in the lower part. And to get the resistance, we in this case were just down to 21 meters. The next number of tests were up to down to 30 meters, and the main piles were founded there down between 24 and 28 meters. And in the case of the full displacement piles, they were typically between 6 and 9, 8 meters depth. Okay, here are the surface wave, the shear waves, and it's clear, noticeable that the blue ones are the best soil, let's say, and here is clear one layer of clay soils. We are in a region with very new quaternary soils, all of them hydraulically deposited, so we can find huge difference in very short distances. I will show one of the benefits of the expanded body is because it measures horizontal stresses, and in very, very small distance, we can find a huge variation, which is almost impossible to get with the soil investigation because of the density or the number of investigation we perform. Now, before following, the last part of the project is in the other slides. I will introduce rapidly what is the expanded body technology. It is basically a folded steel tube that is attached to the bottom of the pile or the anchor, and then you expand. You expand it injecting grout. So we can expand from 120 millimeters up to 800 millimeters. So you can imagine that at this depth, the final force because of the pressure is immense, and that produces a perfect spheric cavity expansion where you can see even each step of this type of expansion. So at the end, you know some geotechnical parameters, and one of the most important things is that this type of technology gives you information in real time of the 100% of the pile tips, which is very important in terms of reliability. So this is the way it expands. We start from 120 until 150 millimeters in diameter, and we go up to 800 millimeters. So just imagine the passive value of this movement is really important. There are some guides in European code, in Swedish codes, and all the criteria of full displacement are applied for the expanded body because it really produces a full displacement action. So we have the system has the folded steel, the injection, the reinforcement, the main injection. We also have, as I will show you, a secondary injection at the bottom of the element, and everything is monitored is instrumented volume and pressures. This is the case of the post-grouting. Normally, when you expand the element, it inflates laterally and it also shortens a little. And during this shortening, the soil moves plastically downwards. But in soft soils, we have noticed that including a post-grouting, we really get better behavior. We use it in terms of settlement reduction. So here you have an exhumed one, and here is the injection curve of this expanded body. Which is interesting is that the maximum pressure is basically the same of the body, which also shows that this spheric expansion works. At some point, it produces a hydraulic failure because if you imagine 2.5 megapascals, it means 250 meters of water pressure. So at certain point, it really overpassing the compacted area, it really produces a leakage in this post-grouting. It functions similar to a large-scale pressure meter. This is why we have used it also as a test device. And I will show you some curves so you can understand much better this question. The expansion, of course, compacts the surrounding soil, which is a permanent action. The stiffness is measured up to 4 diameters from the center, and it's still important. And the real-time monitoring increased very much the quality control and performance. We can use it in any type of construction method. The typical thing is drilling, installing, concreting, grouting, secondary grouting, and there you have everything in full. The installation methods, okay, here are some of them. We have installed in drill piles with vibratory system, with a small equipment for underpinning, and in one case in Sweden, it was installed with a jack because they even had no place for the small equipment, and they crossed the soft clays down to a granite, and so it works very, very well. So it's very flexible. And the mechanism, what it happens is it expands, the length shorts a little, and the soil is very, very highly compacted up to the limit. So that's why we are looking for the limit pressure as in the pressure meter test. These type of things produce directly a cost reduction because the first mechanical benefit is that you are increasing the size of the toe of the pile. So the first thing is that your base is larger. But the second one is that you are compacting the soil. So you are increasing dramatically the shear resistance. So that's why it can provide a much higher resistance to in Micropiles is immense, and in other piles it's at least the double of the regular resistance. So it can help you to shorten the length or to reduce the diameters. And in any of those cases, you have less excavation disposal, you have lower equipment usage, you have lower volume material consumption like concrete and steel. So altogether, they produce a very clear and direct economy, and also the time of the construction. Of course, we can transform that, as I will show you, not only in money, but also in carbon footprint, which in some places is a critical question to take in account. The time savings is from all the point of view, very, very easy to notice. And typically, the carbon footprint reduction is about 50%. But in one case where we installed several micropiles, the carbon footprint was, the reduction was 84% because we did it in a very, very fast way, and the material consumption were very low. We use slender micropiles, and it was a very good example of CO2 emissions reduction. And the other important thing is that the quality control is not something you have to decide to use it or not. It's mandatory. The system works with this quality control system. You have to measure pressure and volume in all the cases. Here, continuing with the Manzana 40, here was 406 piles of 280 metric tons of service loads, and a real time with all the expansion process, and 817 full displacement pile with 80 tons. The typical pile for the same geometry of this full displacement pile, the drill pile in the same conditions, is around 35 tons. So here we double the capacity of the piles. We performed for the main project 9 load test, and in all those were quality control tests. It means that we were looking for the real behavior and to check if the deformations were into the range. The reality is that for the project deformation, those piles achieved more than 400 tons instead of 280. Here, if we get to the 10 millimeters, we get 400, and here we will get 440. And that was the same with the other test. So and that's because in advance we really cannot know exactly the stiffness improvement we will get with expanded body, and it is always in the safety side. This is a typical report made for each block. In each block, we have, okay, let's say 20 piles or 22. In other block, we can have 100 piles. So for each block, we make a report with all the variable pressure, volume, what is the friction, the calculated friction in the shaft, and so on. And then we compare the resistance of the project, the calculated resistance of the project for this block, against the resistance we get calculating with the expanded body values. In general, we get, of course, higher values. But it's also very interesting if we suddenly find that in one of the blocks or during the installation, the resistance is lower than the one of the prediction. And that's important because as we have those sedimentary soil with such a level of variation, in those cases, it's very easy to intervene and to reinforce the element. Even in bridges, we have reinforced just installing a couple of meters deeper. Here is a brief resume of the process. And here we pass. The original project was designed with 600 millimeters drill and the bentonite piles with 150 tons only. We got from the 760 piles of the original project to 406, and with 2,800 kilonewtons. It meant that 49% of time reduction, a cost reduction of 32%, and a carbon footprint reduction of 61.4%, which is important in all the sense. So thank you. I would have presented more things, but I have a couple of unfortunately, I haven't more time to present, for example, a series of curves where you can see that in one block of 5 times 5 meters with 13 piles, we had difference of 100% of the injection pressure, the maximum pressure. In one place, it was 25 kilograms per square centimeter, and in another place, it was 51. So that is, for me as an engineer, is great to know this difference. For some designer, is complicated because they ask, so how are we going to design? And in this type of soil, that is a very, very tricky question because we can have such difference in very short distances. But anyway, one of the benefits is that if we decide with the prior soil investigation, the place where we want to install the expanded body, we can use a sacrifice expanded body for a soil investigation. We install, we expand with water, and we get all the pressuremetric parameters that are needed for such a design. And the last comment is that the name of increased testing saves money. I agree totally. But I would like to do something a little more forward. Increased knowledge save money. And what we want to do with this technology is that testing the 100% of the tips of the pile with a pressuremetric device, it really can save money and headaches because not always is possible to get such level of information. We have another technology. Okay, that is like a Osterberg cell, but for the 100% of the piles with the same philosophy. If we need the behavior of the 100% of the pile, we can really save money in safety factors, in materials, and so on. So I am open for questions, and thank you very much for the invitation.
Thanks, Mario. And as chair of the Sustainability Committee, I'm very happy to see that you made this statement about as reducing the carbon footprint and come up with a more sustainable solution that actually also saved money and shortened the schedule as well.